Okay, hello everyone. This is a demonstration video of the Dendro platform. Dendro, the name originated from the realm of trees, from the domain of trees that start as a small seed and then grow up to be large structures with many ramifications. So, um, this demonstration is a short video to depict the main functionality of this platform. Dendro is different from other research data management platforms in the sense that it it uses ontologies on the core and dispenses the need of an underlying relational database as well as the mapping processes and endpoints that are often present in this sort of solutions. So I will show you the ontologies that are used in the inner workings of Dendro. Dendro has its own ontology, as we can see here in Protege. It is loaded in this window here, and it has its own classes. Let's see here, only the active ontology. As you can see, we have um, particular notions, for example, information elements, which has a subclass of repository and external repository. For example, this would indicate that this is a Dendro instance. This example, as well as the external repository, for example, if you want to represent a resource that is not a repository, that is not a Dendro instance within the system, you will use this class, or you instantiate this class. This ontology, therefore, includes notions that were not present in other ontologies and that we required in order to specify our inner model, our inside model of the system. We also have notions like project, for example, which is an experimental project. This will be the instance of a research project represented in Dendro. Dendro also uses other ontologies like the Nepomuk file ontology and NIE ontology, for example, to represent the different file types present in the system, as well as the as its structures, for example. So the full data model is built on existing ontologies. Whenever there is not an existing ontology, we have designed our own classes and properties to represent the notions that we needed in order to make Dendro work. Since Dendro is designed to allow modular growth of the data model without requiring any programming, that was one of the goals, and we needed this flexible data model to represent datasets from different domains, because it's unreasonable to believe that a dataset, that all different domains can be encompassed in a single ontology. We have designed some lightweight ontologies to represent metadata associated with the research, in particular, generically in scientific research, and also the ontologies, the particular ontologies that are modeled for each domain. For example, we have specified the research ontology. It's a very simple, we call it, but it has been coined, the notion has been coined in the literature. We have the lightweight ontology that has, for example, research asset, which can be an experiment or a paper. This is maybe controversial, but we see paper as one of the stages of the research activities. For example, we have these notions that can be mapped as a part of an experiment, and that can be reasonably or semantically mapped to a file or a folder in this case, because in many cases, at least in our experience, many researchers represent their directory structures as parts of their experiments. So that's the main logic behind this data model. We specify these notions that are present in many research domains. This is a research ontology. We have simple properties like for example instrumentation, which is the names of the instruments used in an experiment, measurements, method followed in experiment, um, the type of samples gathered, and the software used for the processing of these experiments. So this is the generic ontology. Let's minimize this. Now, we particularize this ontology and we extend this ontology for two different domains to illustrate our purpose, our demo. Um, the thing is, this can be generalized to different models, to different domains. The curator or the person that parameterizes the Dendro instance can extend the research ontology that I have shown in this window here, protege window. These notions can be extended and particularized according to the research domain. That's our goal, to give interoperability and to allow the data model to grow, taking advantage of the possibilities for ontologies. So we have this ontology here called DCB, which stands for Double Cantilever Beam Experiments, and this ontology is intended to model the domain of fracture mechanics experiments, which is a group that has collaborated with us in our in the development of this platform and former platforms in the semantic technologies. And these experiments were related to some fractures in some samples, fracture analysis in the samples. So let's restrict this. Okay, as you can see, we have extended the DCB experiment. The goal of this is to allow, so semantically they are very close, but the point here is to use these subclasses more like tags for the experiments to allow the system to recognize or to give assisted search for people that are specifically interested in DCB experiments to find them more quickly. Of course, this is an option. This is a bit of a bending the rules of ontology modeling, but we believe that the end result is advantageous. Of course, this can be discussed. It's one of the things that we would like to discuss in a demo, for example. So this ontology also includes data properties, such as, for example, the moisture. This is a metadata, imported metadata value that can be associated to datasets in this particular domain, which is relevant for them for researchers from this domain to understand the moisture percentage of the location where the experiment was carried out. We have also notions like temperature and very particular notions like test velocity, which is these notions are useful for these researchers in the sense that it measures the speed at which the sample was broken. This is very important for them according to our studies. We also have very specific domain properties. This can be used to annotate the datasets, and this demonstrates the applicability of ontologies to generate to allow researchers to use very specific metadata descriptors in description of their own datasets. We also have another ontology in this window. Let me minimize this. We also have another ontology here that is from the analytical chemistry domain, this is from another department at our university. This analytical chemistry domain is related to pollutant analysis. They perform analysis on water and sediment samples that they take from various parts of the country. We are not allowed to say more about the dataset for now. But we have studied with them in order to model their requirements. As you can see, we have a subclass of experiments, which is run. That's the name they give to their own experiments. And we also have a legislation document because they require the usage or the comparison. It's interesting for them to compare the values that they record with the current legislation values for the maximum concentrations of certain compounds, for example, certain substances, dangerous substances. And we have decided to model this class because this can be interesting to give this class to specify that a resource within Dendro, within their Dendro instance, can be an instance of a legislation documents, and it makes it easier for people to find resources that are considered legislation documents in the faceted search functionality, for example. We also see the data properties, which are rather simple. We have a strong emphasis on simplicity here. We don't model ontologies in the typical sense that we see in many ontologies that go deep into the specific notions that are present in each domain. We prefer to stick to simple data properties because we know that the simple models are we have to use simple models in order to make it easier for researchers to use this sort of system and to ensure the cross-domain applicability of this approach. So now that we have covered the modeling of the ontologies, we now show the usage of these ontologies in the operational system. Here we have a Virtuoso OpenLink Virtuoso instance. This is the open source version of Virtuoso of the Virtuoso Triple Store. As we can see, we have this is the list of graphs present in the system. In this instance, we have two ontologies. We have the main Dendro ontology, let's say the core ontology, the first one that I showed in the modeling part. Now we have the DCB ontology. The other ones are also loaded here, but sometimes the graphs do not appear in the graph list. It appears to be random. So, we can see from if we perform a simple query, for example, in this area here, we can see we can perform a simple query to ensure that the triples are there, even though they are not listed. Even though the graph is not listed, we can see that it is present. You see the DCB experiment class, for example, present in this triple. So each ontology is loaded in its own graph. We can see the research ontology being loaded, even though it was not listed in the graph list. It is here, and it is successfully loaded. This is necessary for the parameterization of the Dendro instance, because Dendro will actively use the ontologies present in the Virtuoso instance that it connects to in order to show more or less descriptors to its users in the annotation of the datasets. We can also see the analytical chemistry ontology being present here. You see very specific notions of the Dendro, of the analytical chemistry ontology in this case. So now let us take a look around the solution, the Dendro solution. As you can see, these are our wishes for the quantity of papers and datasets. We hope someday Dendro will aspire to do this. So the first step is to log into the system. I will sign in with my login, my password. This is the project list. We have the option of creating a new project. Okay, I can show you how to create a project. Test. Project description test project for the demo. Okay, all these values. The importance is all these values are stored in the triple store. As you can see, I can select, for example, if I go here. This is the name of the default graph. Okay, this is already a very large graph, so it took a while. This is the main This is the main graph, and I will show you, just to prove that this is really using the triple star. I can I know that new project will be what is the handle we are giving it? It's project test. So if I query for project test, I'm asking for all the triples that have project test as their subject, the result will be an empty result. But after I create the project, okay, so the new project was created, and we can see that new triples are added for this project. So this is really using triple stop. It's not a hoax or something like that. So now, but since we have created a blank project, I will show you an already loaded one. We can go into this project just to show you that the project is empty. No, nothing is present in this project. We can add folders. For example, base data, and base data folder is added. We can see, for example, I know the roots because, well, I participated in development. So data, let's see, we have to deal with the escapes. Let's see if I can get this right. Okay, so I have to escape because every URL is escaped, so I made the escape myself. We can see that the new folder was created and it was modified at this time, at the present time, at the recording of this video. It is of the type NFO, which is the Nepomuk file ontology folder. We are using ontologies to represent our everything in the data model, as you can see, and it is now present. Now I have to get into the base data folder, and we now are in the project folder. I can upload files to this directory. Let's, for example, upload some files. Let's upload the ontologies, the OWL files. For example, we open these. And they are loaded in this directory. This tool is still under development, so we still have to put some nice icons here to improve this. If we want to add any metadata to this folder, how will we do this? We have the possibility on the right of selecting descriptors. For example, I am in the base data directory. This value here is using the NIE title property. It's not using the Dublin core property because to give the flexibility to the users to specify the title of this folder or this experiment. It could be an experiment folder, for example. We can add it. We can add the title, the metadata, for example. We can insert, for example, the title of the base data folder, for example, and this will be the title of this folder. This will be recorded as the title of this folder. As you can see, when we select a descriptor from one of these smart descriptors, so to speak, this active descriptor group selection will become active, and we now are restricted. These smart descriptors will be restricted to the ontologies present in the DC terms ontology. As the DC terms ontology were already the descriptors there, you do not see any change, so I will illustrate this better. We have this autocomplete box that allows users to specify, to fetch additional descriptors from other ontologies, coming from different ontologies modeled after each domain. We can, using this autocomplete box, we can specify, for example, um, we can, through the autocomplete box, fetch descriptors from the DCB ontology, for example. This is getting quite slow because I'm using my MacBook to record this video, and sometimes it blinks because the CPU is at 100%. So I can use this to put in additional descriptors. When I press the Enter key, you see the DCB namespace has been added, but as the DC terms is also added, nothing happens in the smart descriptor because this is an OR of these active descriptors. I can specify the specimen length, for example, 280 millimeters. I can remove the DCB, the DC terms namespace, for example, and watch what happens to the smart descriptors. Now we only have descriptors from this ontology. This needs a bit of improvement, yes, but as we can see, this is being restricted according to the namespace of the ontology to make it easier for the researcher to specify additional ontologies, additional metadata values from this DCB ontology. The goal will be in time for the curators to specify different ontologies, and the researchers would be able to see their own notions being specified here, or the notions that are specified with the collaboration of the research, of the curator in this case. So now we can save our records, and we can go to the changelog to watch what happens. Okay, so now we have added the two metadata values, and now we can see, or we can confirm the modifications, or we can track changes and see the different updates and different changes made by each user, as this is supposed to be designed to be a collaborative tool. We can see this the list of changes and the list of versions, and also the list of descriptors that were modified in each version. For example, in this first version, I have modified the title value and the specimen length value. If I go back to the information area, the metadata editor area, this is, I'm sorry, this is really slow because my computer is quite old, and this is running a virtual machine and running the server and all this in my laptop, and also recording the screen, so I'm sorry. So if I, for example, if I edit one of these values, let's see, instead of 280, it's 300 millimeters, for example, I can save the value, and when I go to the changelog, the descriptor will be shown as modified, not added. That's something that we have added to have the right granularity to record every change in every descriptor individually, as you can see. We have the change of the descriptor. Going back to the information area. Okay, going back to the description area. If we delete the title, for example, we can delete the title. We save the record, and we go back to the changelog. And as you can see, every single operation is recorded using recording the timestamp, recording the author of the change, and recording a brief summary of each change. For example, the first change I made included the inclusion of the title and the input of the specimen length. After that, I changed the specimen length to 300 millimeters, and then I removed the title and then edit it back up again. So this is this shows the distinction between each of the operations. This is recorded in the system. So let's imagine that we want to see in the SparkQL interface the data that is recorded in this screen, or the underlying data. In the triple store, we can say that, for example, um, uh, we are looking for the changes of this on this resource, on this folder. For example, we can say that ask for the versions of for this of this folder. We have four versions, like stated in the list. It's the same data. It's just to show you that it's using the triple store and how it is represented. We have the list of versions, and we also, if we want to see each change, because each change is a resource. That's how we have these different distinctions, types of change, and types of changes, and the old values, the new values. If this represents a removal, the author, all this. I believe this is the property. Yeah. So here we have, for this version, give me all the changes that pertain to this version. And now we can ask for the different properties in each change. For example, we want the change, we want the properties associated with change, and then the object. And as you can see, we have the change. The triple star states that this is a change. This is a change in a resource. This is qualified in our ontology. We have the timestamps of creation, modification. We have the version to which each change pertains to. This is the property. We have the type of change, for example. This is how we can tell the different types of change present in the system, in each change. The new values, for example, this pertains to different changes. So we have, for example, for change 1, we have the old value, 280 millimeters. For the same change, the new value is 300 millimeters. That's how we can say that the old value is 280 millimeters and the new value is 300 millimeters. So no tricks under the sleeve. This is really using triple star for everything. Of course, this allows for very flexible querying. As our model is specified using ontologies, Dendro makes ontologies available, and even other programmers and even external systems, when this goes live, will be able to query the database directly if we want to give permissions to those external systems, of course. Permissions and parameterization is a very important part of Dendro. As you can see, we are only showing some of the facets. We have implemented facets in the code itself to restrict certain descriptors to give to specific actions, not to allow even the APIs to access the specific values of descriptors. For example, I can give you an example. This is the code. It's written in Node.js, and as you can see, I have, for example, for the descriptor deleted, which is an element of the DDR platform. Of course, this for now is written in JSON, this parameterization, but in the future we hope to put this parameterization in the ontology itself. As you can see, it's not very hard. It's just a matter of writing the code and the queryings, the different queries to access Virtuoso instead of having this hard-coded in this file. But as you can see, we have these different attributes that specify for each descriptor if it is accessible or if it is returnable in the function that returns the value of this descriptor. The function, if the value of this descriptor, the parameterization, is not within some of these specifications, does not have these attributes, some of these descriptors will not be returned. This way, we can have in the future we can give control to the users, to the system administrators, to enable or to show or hide the values of certain descriptors even in API calls. Speaking of API calls, I can give you an example of an API call. For example, we see these here in this sidebar. We see the contents of the files and folders. Yeah, this is getting really slow because my computer is slow. So now, if I wanted to access the contents of this file, this folder, for example, on a tablet, on a smartphone, on a different device, I could type, for example, ls at the front of the URL, and the server will understand this and give me a JSON reply. Of course, in the future, we are planning to give these replies also in the RDF. That would be the ideal linked open data scenario. But for now, we are doing this only in JSON for API purposes. All the functions like creating a folder, deleting a folder, backing up a folder, restoring a folder, it's all available in API format as well. Because as you can see, the interface is built on heavily on JavaScript, and it uses AngularJS for all this management of generating the interface. If we want to add another folder, just to illustrate to you the deleting function, we can see, for example, folder to be deleted. Yes, we can go in the folder, and then we can upload a file to demonstrate this. By the way, the storage layer is built using the file storage layer is built using and GridFS and MongoDB for scalability purposes. We allow the biggest files to be stored in this system, provided the user is ready to wait for the uploads and downloads. But that occurs in any system. So we upload a new file. As you can see, the file was uploaded. Also, whenever a file is selected in this interface, the metadata that is added is not added to the folder, but to the selected file record. So going back to our project list area, we have shown creating a project from the start, but we also have another project now fully filled in, which is a good example of a practical application. As you can see, this contains, for example, the history changes of the project, all over the project. In this case, we see the recent changes on the right side with the authors and the respective resources that were changed, the respective folders or files which the metadata was added or manipulated. We see the statistics in this project. We see this is calculated directly using the MongoDB database to show an overview of the size of the project at any given time. On the left side, we have the data explorer showing the list of the files and folders present in the present file. We can create a new folder, we can upload new files, we can download the complete folder. This will create a zip file containing the complete structure of the folder's present folder and give it downloaded to the user's computer. This is a backup operation. It's the same as a download operation, but we'll place a metadata.json file at the root of the zip file that can be used to restore the contents. Like we edit metadata, we add files, we delete files. If we restore a backup package, the files, the complete directory structure will be just as it was at the time of the last backup. Every change is reversible. For example, if I delete a folder, If I delete a folder, it is signaled as deleted. For now, we have this. We are now working on the real delete, really deleting files. But for now, we are adopting a Dropbox-like policy of not deleting, and you will have to manually delete the past versions. If we go into the file, into the folder, I mean, we see that the file that was inside is now deleted as well. So when we delete, everything inside is deleted, is signaled as deleted, and we can hide or show the files that were deleted using this option here. So now we can undelete this folder. And go into it. And now, well, there's not much more to say. This description area, you may notice that the control for this description descriptor, or to allow the user to specify the description of this folder, this is the DC description value, to be precise. This is the description property of the Dublin Core ontology. This appears as a markdown box, so it allows users to write in markdown syntax. For example, we can specify bold, we can specify italic on different words, and when we save this syntax will be saved to improve a presentation, for example. As you can see, this is a small touch we gave to the solution. We have, as you can see, specific descriptors. This is a full description with the values that have been confirmed with the researchers that have been helping us in this work. As you can see, we also have a search box. For example, let me put here a word that I know is present in these descriptions, for example. And as you can see, we have two hits. One, which was the base data folder in the DCB project, double cantilever beam. We can see all the properties. These are indexed in the Elasticsearch cluster that is running, also supporting this free text search is an Elasticsearch cluster. We could use the free text search functionality in Virtuoso, but we have decided to opt for Elasticsearch to give us more flexible capability over the free text indexing. Also, this Elasticsearch is very good because it scales, and we are preparing the system to be able to scale to handle even small and large projects, even though this is targeted at long tail of research of science. We can see that second hit has been the base data, maybe because of this description having data in its literal title of the DC ontology. We can see that every single literal is indexed. This is done automatically. Whenever we add new descriptors, whenever we remove descriptors, the document is re-indexed in Elasticsearch, so this is always up to date. This is an important aspect to take into account, as this is a collaborative platform. It is designed to be collaborative, and this has always to be evolving and being always up to date to the index. So this is Dendro. It is a fully linked open data and triple store based platform using Node.js, AngularJS, Elasticsearch for the free text indexing, GridFS for file storage, and OpenLink Virtuoso for SparkyWell querying and triple store. Thank you very much for your time. I hope you enjoyed this small, not so small demonstration.